Hello Calc 3, welcome back to another video. The goal of this video is to give some example problems related to the material from chapter 12 and 13 in preparation for exam 1. So let's get right into it. The first question is asking us to prove a property of the cross product. So we are going to prove that R times S, where R and S are scalars, times the cross product of u and v is equal to r times u, the cross product with s times v. Okay, so let's get right to the proof. In this case, we're just going to calculate the cross product of both sides of this equation and show that that the two calculations are equivalent to one another. So to do that, we can write each of our vectors u and v in component form. So u is equal to u1, u2, u3, and v is equal to v1, v2, v3. And now let's calculate both sides of this equation here. So u cross v is going to be equal to the determinant of the matrix given by ijk in the first row, then u1, u2, u3 in the second row, and v1, v2, v3 in the third row. So let's calculate this determinant. We get I multiplied by the determinant of u2, u3, v2, and v3 minus j times the determinant of u1, u3, v1, v3 plus k times the determinant of u1, u2, v1, and v2. And now we can calculate the determinants of each of these 2 by 2 matrices, and we find we have u2, v3 minus v2, u3 minus j times u1, v3 minus v1, u3 plus k times u1, v2 minus v1, u2. So this is the expression giving us the cross product of u and v, and the left side of our equation is r times s multiplied by the cross product of u times v. So r times s times u cross v will be equal to r times s times the vector from above. So u2 v3 minus v2 u3i minus u1 v3 minus v1 u3j plus u1 v2 minus v1 u2 k. And of course we can just distribute the scalar r times s through all of this, and we end up with r times s times u2 v3 minus v2 u3i. And I'm wondering if we should probably distribute the r times s even through there. So instead I'm going to write rs u2 v3 minus rs v2 u3i minus u1, or excuse me, r3 or rs u1 v3 minus rs v1 u3j plus rs u1 v2 minus rs v1 u2 k. And that looks like it's about as expanded as we can possibly get it. So now let's move on to the right side of the equation. Let's calculate that and see if we can get it to look like the equation that we just found, or the expression that we just found. Okay, so r times u in component form is going to be ru1, RU2, RU3, and SV is equal to SV1, SV2, SV3. So now let's find RU cross SV, and to do that we're going to calculate the determinant again of this 3 by 3 matrix. So we have RU1, RU2, RU3, and then SV1, SV2, SV3, and we find, let's see, we have I times RU2, RU3, SV2, SV3, minus J times RU1, RU3, SV1, SV3, plus K times RU1, RU2, SV1, SV2. And now let's make this look nicer by calculating the determinants of each of these 2 by 2 matrices. Okay, so it looks like we're going to get, yes, so we're going to get RSU2 V3 minus RS V2 U3 I minus RS U1 V3 minus RS V1 U3 J, and then finally RS U1 V2 minus RS V1 U2 K. So now we've calculated the right side of the equation, and we get the resultant expression here. And if we compare this expression with this expression, we find that they are equivalent with one another. Yeah, let me just double check that I did things right here. Yeah, so they're both equivalent with one another, and because we found when calculating both sides that the resulting expressions are equivalent, we have therefore proved, and I'll write this down. So we can write, therefore, R times S times the cross product of U and V is equal to the cross product of RU and SV. Okay, so the reason that I wanted to go through this example is to give a general methodology for proving a property. In this case, we expanded both sides of the equation until we found expressions that were equal to one another for both sides of the equation here. It's also possible in a lot of different cases when you're proving a property to take one side of the equation and expand it or just manipulate it until you get it to look like the other side of the equation. In this case, we manipulated both sides. But there are different methodologies to proving. This is one of them. All right, for the second example, we are going to apply the dot product to prove whether or not given vectors are orthogonal. So the question, we'll start off with part A, is to prove or disprove that the vectors -1, 2, 1 and 2, 4, 8 in component form are orthogonal. So let's start off with that. To do so, we're going to take the dot product of the two vectors. So -1, 2, 1 dotted with 2, 4, 8 is going to give us a -1 times 2 plus 2 times 4 plus 1 times 8, which is equal to -2 plus 8 plus 8 is equal to 14. And now we would just say, because the dot product is not 0, -1, 2, 1, and 2, 4, 8 are not orthogonal. Okay, so that was part A. Now we can move on to part B, where the vectors will in fact be orthogonal. So again, we're going to take our two vectors, take the dot product. Let's see, 2, 1, 0. So the dot product will be -1 times 2 plus 2 times 1 plus 1 times 0, which is equal to -2 plus 2 plus 0, which is just equal to 0. So in this case, we have the dot product equaling 0. So because the dot product is 0, -1, 2, 1, and 2, 1, 0 are orthogonal. So in this case, we ended up proving that our two vectors were orthogonal. So these are the two kinds of cases that you're going to find for problems where you are trying to prove or disprove that a pair of vectors is orthogonal. Okay, so for our third example, I want to calculate the distance from a point to a line in space. I wanted to go through an example like this because I didn't put one on either of the quizzes prior to exam 1. So in this case, we have a line L, and it's passing through points 2, 0, 1 and 1, 3, 2, and we want to find the distance from the point 3, -1, 0 to this line L. So let's see if we can find a solution for this. Well, we are given the formula that the distance between our point 3, -1, 0 and the line L is given by the magnitude of the cross product of the vector from P to S and V divided by the magnitude of the vector V, where S is the point 3, -1, 0. P is some point on the line L, and V is a vector parallel with L. So we're going to need to find some point on our line L, and we also need to find a vector parallel with L. So the point on L, well, we're given that L passes through the points 2, 0, 1 and 1, 3, 2. So we can actually just choose either one, whichever one we want. So I will pick the point 2, 0, 1. That's going to be our arbitrary point lying on the line L. And now we also need a vector parallel to L. And one such vector would be the vector that connects the 2 points that are both lying on the line L. So let's find the vector connecting the points 2, 0, 1 and 1, 3, 2. And we can find that just by subtracting the components of those 2 points. So we have 1 minus 2, 3 minus 0, and then 2 minus 1 as the components of this vector. And we can simplify that a bit and make it -1, 3, 1. So a vector parallel to L in component form is given by -1, 3, 1. And from here we need to find the vector from P to S, where again P is this point on the line that we specified up above. And we can find that in component form by taking 3 minus 2 as the first component, -1 minus 0 as the second component, and then 0 minus 1 as the third component. And again, simplifying, we get 1 minus 1 minus 1 as the vector that goes from the point P on the line to the point S. And now we want to calculate the cross product of this vector from P to S with the vector V that is parallel to L. So let's do that. And to do so, we're going to calculate the determinant of this 3 by 3 matrix. Let's see, we have a 1, a minus 1, a minus 1, and then for V, we get a minus 1, 3, 1. And now let's calculate the determinant of this 3 by 3 matrix. We get I times the determinant of minus 1, 3, 1, minus j times the determinant of 1, minus 1, 1, plus k times the determinant of 1, minus 1, 3. And now let's calculate the determinants of each of these 2 by 2 matrices. We get a minus 1 plus 3i minus a 1 minus 1 j plus a 3 minus 1 k, and ultimately this gives us the vector 2i plus 2k. Okay, and we want to take the magnitude of this vector. So the magnitude of the cross product of PS with V is equal to the square root of 2 squared plus 2 squared, which is equal to the square root of 8, or 2 times the square root of 2. So that gives us the numerator for the formula giving us the distance. And now we need the denominator, or the magnitude of V. So the magnitude of V is given by negative 1 squared plus 3 squared plus 1 squared, which ends up being the square root of 11. And now, using the formula from the beginning of the problem here, we have that the distance from the point to the line is given by the cross product of PS with V, or the magnitude of the cross product of PS with V, divided by the magnitude of V. And we just calculated both of these things. So we have 2 times the square root of 2 divided by the square root of 11. So this would be the distance from the point 3, minus 1, 0 to the line L that passes through the points 2, 0, 1 and 1, 3, 2. You should note that these kind of problems can be different depending on what kind of information you're given at the beginning. So instead of characterizing the line by telling you what points it passes through, I could characterize the line by telling you a single point that it passes through, and then a vector that's parallel with the line, and that would make the problem a little bit simpler because that information better corresponds with the formula directly for the distance from the point to the line. But this example is probably a little bit more instructive. There's a little bit more work to do, but it shows how we can get the information about L just given these 2 points that L goes through. All right, for this next example, example 4, we want to find an equation for the line of intersection of 2 planes. So we are given the 2 planes, 3x plus 2y minus z equals 7, and then the other one is x plus 3y minus 2z is equal to 7. And we want to find parametric equations that describe the line of intersection of these 2 planes. Again, I wanted to give this kind of problem because I don't think that it was covered on either of the quizzes. And it's a relatively difficult problem with its own kind of method for a solution, so we might as well go through it. So to find the parametric equations for any line in space, I need 2 things. So I need a point on the line of intersection, and I need a vector, which I will call V, parallel to the line of intersection. And once we have these two things, then we should just be able to write down immediately the parametric equations describing the line of intersection. So let's start off with finding the point. Well, a point that's on the line of intersection is just going to be a point that satisfies both the equation for plane 1 as well as the equation for plane 2. So we need to find a point that satisfies both equations. Immediately, if I just start thinking of, what point is going to both satisfy 3x plus 2y minus z equals 7 and x plus 3y minus 2z equals 7, that's a little bit tough maybe to come up with a point right away. I think if you think about it long enough, you can probably find one without too much trouble. But to simplify the problem, we can just say we might as well find a point where the z coordinate is equal to 0. So again, we're just looking for any point that lies on the line of intersection, and to simplify this, we might just say, well, why not find the point where the z coordinate is equal to 0, or the z-intercept. So the point is going to have the form x, y, 0. And what this does to help us is it simplifies the equations for both of the planes above. So if we assume that z is equal to 0, then the equations for the two planes become 3x plus 2y is equal to 7, and x plus 3y is equal to 7. So now we have two equations and two unknowns, x and y, and we want to solve for x and y. And once we do so, then we have a point that's going to be on the line of intersection. So it looks like we can multiply the second equation here by 3 and then do some cancellation. So 3 times x plus 3y is equal to 3 times 7. That gives us 3x plus 9y is equal to 21. And now I can subtract this equation here from this equation, and that will allow us to cancel out the x's. So 3x plus 2y is equal to 7 minus the equation 3x plus 9y is equal to 21 is going to give us 7y, or negative 7y, is equal to negative 14, which implies that y is equal to 2. And now we can take y equals 2 and plug it back in for either of the original equations, and it tells us that x is equal to 1 when we do that. So the point 1, 2, 0 is on the line of intersection. So now we have the first piece of information. We have a point on the line. Now we need to find a vector that is parallel to the line of intersection. Okay, so the line of intersection is going to be normal to both the normal vector of the first plane as well as the normal vector of the second plane. It's going to be orthogonal to both of them, or perpendicular to both of them. So if we can find a vector that is orthogonal or normal to both of the normal vectors of our two planes here, then that vector is going to be parallel to the line L. And fortunately, we have a nice way to get a vector that is orthogonal to both of the normal vectors. We can take their cross product. So I'm going to call the normal vector of the first plane n1, and I'm going to call the normal vector of the second plane n2, and the cross product of these two normal vectors will give us a vector parallel with our line of intersection. So we need to figure out the cross product here, And to do so, we're going to take the determinant of this 3 by 3 matrix, ijk, in the first row. In the second row, we have the normal vector for the first plane, which we can just read from the equation is 3, 2, minus 1. And in the last row, we have the normal vector for the second plane, which again we can read from the equation is 1, 3, minus 2. So let's calculate this determinant. We have I times the matrix 2 minus 1, 3 minus 2, minus j times the matrix 3 minus 1, 1 minus 2, plus k times the matrix 3, 2, 1, 3. And we can make that look nicer by calculating the determinant of these 2 by 2 matrices. So we get a minus 4 plus 3i, and then a minus 6 plus 1j, and then plus 9 minus 2k. And let's simplify this a little bit more. We get negative I plus 5j plus 7k. So v, or the vector that is parallel with the line L, is going to be minus I plus 5j plus 7k. And now we have both pieces of information that we need. We have a vector parallel with our line, and we also have a point on our line, and from here we can just write down parametric equations. So parametric equations for the line of intersection are x is equal to 1, because 1 is the x-coordinate of the point on the line, minus t, where we get this minus 1 times t, because minus 1 is the I component of our vector v. Then we get y is equal to 2 plus 5t, where again 2 is the y-coordinate of the point on the line, and 5 is the j component of the vector v. And then finally, z is equal to 0 plus 7t. And t is going to be ranging from negative infinity to positive infinity. So these are parametric equations describing the line of intersection of the two planes that were given in the problem. Yep, so that's nice. Alright, so now let's move on to the last example for this video, example 5. Example 5 covers some concepts that haven't been covered in the other videos, and they haven't been covered on the quizzes either, so I do want to talk about it a little bit here because I think I'm going to put it on the first exam. And so if you're still watching this video at this point, it is certainly to your benefit, as this last example is basically going to serve as a prolonged hint to at least one question on the exam. So without further ado, let's get into it. So the ultimate goal of the problem is to find the maximum speed of a particle that's traveling along some segment of curve in space. And now in particular, we're given the curve r of t is equal to t squared I plus cosine tj plus sine tk. And again, this is some curve in space, and it gives the position of a particle in space from time t equals 0 to time t equals 2 pi. And our goal is to find the position of the particle when its speed is the greatest along this curve, or this segment of the curve. So ultimately, we want to find some time, which I'm going to call t naught, such that the speed of the particle is greatest at t naught. And then the position of the particle that we get by plugging t naught into the position function, this is going to be the position of the particle when its speed is greatest. So the real involved part of this problem is just finding this value for t naught. So let's see if we can do that. First, we need a way to describe the speed of the particle on the curve. So we know that the speed of the particle is equal to the magnitude of the velocity of the particle at different times along the curve. And we also know that the velocity of the particle is going to be given by the derivative of the function giving the position of the particle. So let's find the function giving us velocity. So we're going to take the derivative of the position function above, and we get 2ti minus sine tj plus cosine tk. So this will be a function giving us the velocity of the particle at different times t. And now we want to find the magnitude of the velocity to give us the speed. And we get 4t squared plus sine squared t plus cosine squared t. We're taking the square root of all of those things. And sine squared t plus cosine squared t is just going to be 1. So this is the same as the square root of 1 plus 4t squared. So now we have a function giving us the speed of the particle at different times t. And we still need to find when this speed is maximal along the curve. But notice that when we're talking about the speed of the particle, the speed is a scalar function. So it takes one real number, which is the time, t, and it outputs one real value. And so the speed is just a function like we would have seen in Calculus 1. So we can take tools that we have from Calculus 1 to find when this function is maximal along the interval from t equals 0 to time t equals 2 pi. So let's apply some of those tools. So we know that the absolute maximum of the function giving us the speed of the particle occurs at the endpoints of the interval from 0 to 2 pi, or at a critical value. So those are the two options. Either the maximum is going to occur at the endpoints of our interval from 0 to 2 pi, or the absolute maximum is going to occur at some critical value inside of that interval. So now we want to look for any critical values inside of the interval, and to do so, we want to take the derivative of our function giving speed. So that ends up being the derivative with respect to t of the square root of 1 plus 4t squared, which is equal to 1/2 times 1 plus 4t squared to the minus 1/2. And then chain rule tells us we have to multiply by the derivative of 1 plus 4t squared, which is 8t. And to find critical values, we want to set this equal to 0. So we have 8t over 2 times the square root of 1 plus 4t squared. And now we're going to set it equal to 0 and solve for t. Well, this expression is only equal to 0 if the numerator is equal to 0. And the numerator is equal to 0 only when t is equal to 0. So 8t is equal to 0 implies that t is equal to 0. And this is going to be our only critical value when t equals 0. And now to find the absolute max, we're going to take the endpoints of our interval from 0 to 2 pi and plug them into the expression for speed, as well as the critical value that we just found. And we're going to see which value or which output is maximal. And that's going to be the time at which our particle attains its maximum speed. So if we plug in 0, which happens to be both our critical value as well as an endpoint, into our function for the speed of the particle, we get the square root of 1 plus 4 times 0 squared, which is just equal to 1. And now if we take the other endpoint of the interval, 2 pi, and we plug it into the expression for speed, we get the square root of 1 plus 4 times pi squared. And I think this is probably as nice as you're going to make this look, the square root of 1 plus 4 pi squared. But this is clearly greater than 1, since 4 pi squared is greater than 0. And actually, once you look at it like this, you could probably, by the time you write down the function for speed above, and you find out that it's equal to the square root of 1 plus 4t squared, instead of going through this process here from Calc 1, you could also say, hey, that equation giving the speed of the particle is always increasing when t is greater than or equal to 0, and therefore the maximum is going to occur at the upper endpoint of our interval. You could also say that as well. Both methods are going to work here. So we see that the absolute maximum of the function giving the speed of the particle occurs at t naught equal to 2 pi. So this is that t naught that we were looking for at the beginning of the problem. And now finally, we want to find the position of the particle when the speed is maximal. So we're going to take this t naught and plug it back in to our function giving the position of the particle. And this is going to be r of 2 pi, which is equal to 4 pi squared I plus, I think cosine comes first if I remember. Yes, so cosine is going to come first. So we have cosine of 2 pi j plus sine of 2 pi k. And now sine of 2 pi is just equal to 0, and cosine of 2 pi is equal to 1. So we get that the position of the particle is equal to 4 pi squared I plus j. And if we wanted to write this as an ordered pair, or an ordered triple, I should say, then the point at which the particle is located is going to be 4 pi squared, 1, 0. So I would accept either the position of the particle given as a vector like this, or you could give it as a point. But yeah, so a problem like this is going to show up on exam 1. Hopefully this acts as a nice hint. The problem is not going to be the same. I'm going to change it up a bit, but this should at least give you a head start on that problem. And the key here is just to apply this concept of finding absolute extrema along scalar functions from Calculus 1. Okay, and that concludes the examples that I wanted to go through in this video. So hopefully that gives you some problems that we didn't cover in other videos or that weren't covered on the quizzes, and it should give you some extra stuff to study before you start working on exam 1.